Good evening and welcome to this Cambridge conversation on Beauty and the Beast, matter, antimatter and the Large Hadron Collider. My name is Andy Neely and I'm a professor at the university, but also hold the position of Pro-Vice-Chancellor for Enterprise and Business Relations. And so effectively across the university, I look after everything to do with innovation, commercialization, startup spin-outs and links with business. And I'm delighted to be here with you this evening and to welcome you to this Cambridge conversation. It's the seventh in a series that's proved to be extremely popular, really trying to bring you ideas from across collegiate Cambridge and explore with you some of the research that's going on in the University of Cambridge. Cambridge has been synonymous with excellence in physics ever since Sir Isaac Newton was in the role as the second Lucasian Professor of Mathematics. It's the same chair that was later held by Charles Babbage and Stephen Hawking. The 19th Lucasian Professor, Michael Cates, now holds it. Cambridge has been at the vanguard of discovery in physics for centuries, and we remain so now. Covering 7 major research themes, our teams work together in a multidisciplinary fashion for which Cambridge is renowned, based at the world-famous Cavendish Laboratory. The first Cavendish Laboratory was opened in 1874. Physics is currently based in the second Cavendish Laboratory that's been in that location since 1974. But we are building the third iteration, an ambitious project that will rehouse the entire department in a state-of-the-art facility to be known as the Ray Dolby Centre, following an incredibly generous gift from the Dolby family at West Cambridge. A major asset for the university, it will enable us to supercharge our efforts, and its wonderful design will enable the cross-fertilization of ideas and the conducting of experiments in conditions perfect for quantum physics and for the exploration of the universe. It is emblematic of our commitment to research at the very highest level and to remaining the preeminent force for physics in the world. It sits the heart of our West Cambridge site, uniting physics and technology for the 21st century and beyond. It will be the connection point for Cambridge and some of the most amazing international collaborations such as the Large Hadron Collider in CERN in Switzerland. The LHC is one of the most amazing machines ever built. Some of the world's most incredible experiments are taking place there, but there are plans to construct an even bigger collider, 100 kilometers long. To explain the importance of colliders, quarks, beauty, charm, and their part in uncovering the mysteries of our universe, we will shortly meet 3 researchers working at the coalface of antimatter and matter. But first, Professor Andy Parker himself, the founder of the ATLAS experiment for the LHC, will talk about the Ray Dolby Centre and why it is so important for innovation, for physics, and for Cambridge. Andy, let me hand to you.
Thank you, Andy. That was a very kind introduction. I think you slightly oversold me. I'm one of the founders of the ATLAS experiment. I think there were 60 of us in the room on the day that we started discussing ATLAS. But let me talk about the Cavendish. As Andy has said, we are a fairly renowned laboratory, and in world terms, we're rated very highly. And of course, we want to stay that way. And we've been in our present buildings since 1974, and they're now well past their design lifetime. They've served us well, but we need to move on. We started the project, and we've already rehoused, in fact, a small part of the department. Our astronomers have their own block, thanks to the generosity of Humphrey Babcock, which is our Babcock Centre for Experimental Astrophysics. We have a dedicated laboratory building for biophysics, and we have some of our researchers in the Maxwell Centre, which has a particular mission to interface to industry. But the vast bulk of the department is now going to move into the Ray Dolby Centre, and that is a massive enterprise. This is a building with almost 1,000 rooms. It includes 4 large research wings, each of which is bigger than any of our other existing new buildings, as well as a basement which has been specially designed to the highest possible specification of environmental control and vibrational control so that we can do experiments in quantum mechanics that require extreme precision. There's also a fabulous public wing which will house our lecture theatres and libraries and event space and exhibitions so that we can bring in the public and other scientists to discuss with us. And the whole building has been designed around the idea of collaboration. And this project was made possible by a fabulous donation from the Dolby family in honor of Ray Dolby, who did his PhD at the first Cavendish building back in the 1950s and 60s, and went on to found the internationally renowned Dolby laboratory, which designed the Dolby audio and video systems, which are pervasive today. Their donation allowed us to lever from our own government a further £75 million, which was announced in the House of Commons by the Chancellor, in order to set us up as a national centre for physics. And we will be housing a facility where we hope that other researchers from around the country will come and use our equipment and do their own work, and of course become collaborators and friends of the Cavendish. And we see this national role as part of the future. Physics is becoming a wider and wider enterprise. It requires bigger and bigger teams, and we see facilities growing in scale, and we wish to be at the forefront of housing and sharing that sort of equipment. We cover a vast range of disciplines. I mentioned the biophysicists who have their own laboratories, but will be sitting with the rest of us in the Ray Dolby Centre. We have themes in quantum experiments, in emerging quantum phenomena, in energy and sustainability, which is based on the Winton Programme for Sustainability, which itself was funded by a very generous donation from David Harding. We have astronomers and cosmologists housed in the Babcock Centre, and we have people working on complex systems and new materials and functioning materials. But today we were talking about high energy physics, which deals with the smallest elements of the universe, the forces that make them operate, and connects round actually in very interesting ways to the largest elements, how our universe began and how it started to evolve. Now, this is my own field of research. I've worked since the beginning, as Andy mentioned, on the ATLAS experiment, which is a general purpose exploratory experiment. It aims to be able to look for and find new particles of any sort. And of course, it's was one of the experiments which discovered the Higgs boson in 2012. We also have a program in neutrinos, which is based in the United States at the Fermi National Laboratory there, where the neutrino beam exists. And some of our scientists have been the leaders of that collaboration, even though it is a US national program. But today we were talking about LHCb, which is focused on the difference between matter and antimatter and how that operates in our universe. It is somewhat surprising, as I'm sure they will explain to you in a moment, that our universe is made of matter and not antimatter. And so there is a lot to discover about how matter and antimatter work and how our universe ended up the way that it does. And so on that note, I'd like to pass over back to Andy to introduce the team. Thank you very much.
Thank you, Andy. There's only two Andys on the panel. We're not going to keep passing between Andy to Andy. But thank you, Andy. That was both inspiring and also appetizing in terms of what's coming. So we're now going to hear from three people, or I will have a conversation with three people involved in work on matter and antimatter, and working particularly with the Large Hadron Collider. So the first one is Professor Val Gibson. She's head of the High Energy Physics Research Group at the Cavendish Laboratory. Dr. Harry Cliff works on LHCb in Professor Gibson's team, and his research focuses on the very rare decays of particles known as beauty quarks. And finally, Fionn Bishop is a PhD student studying charge parity violation in particles that contain beauty quarks. So we'll have a conversation for about 20 minutes or so, and then there'll be a time, as I said, to pick up any audience questions that you wish to send in as well. So let's start, Val, with you. And just to give us some background, really, we've heard about the Higgs boson already. It was discovered in 2012. Probably the greatest development in physics this century. Of course, its discovery in itself raises further questions. So tell us what's happened since 2012, what's happening in particle physics, and more particularly, what's happening at CERN.
Okay. Well, thank you, Andy, first of all, for inviting us to have this conversation. And hello, everyone. It's nice to be here. Just on the Higgs boson itself, the discovery was really a monumental leap in our understanding of the most fundamental particles and forces of nature. And it actually, the word particle and force are all encompassing words. I just want to unpick that a little bit, because particles and force are tiny bunches of energy in this very small world that we live in, the quantum world, which contains fields. Now, we've all experienced the effect of fields. For example, if you've got two magnets and you try and bring them close, they either attract or repel, depending on their orientation. And Faraday was the first to experimentally observe a field by placing paper on top of bar magnets and sprinkling on iron filings and seeing the resulting pattern of the field lines. So particles are also related to fields. So for example, the electron, which was discovered at the Cavendish at the end of the 19th century, is an excitation in an electron field. And the photon, which is responsible for the light that we see, is a bundle of electromagnetic radiation described by Maxwell's theory of electromagnetic fields. And the Higgs boson is similarly an excitation in the Higgs field. So actually, the discovery of the Higgs boson is a discovery of a new type of field on par with gravity and the gravitational field. And it's also very special because it gives mass to the other particles as they pass through it. So what we do at the Large Hadron Collider is we collide particles, which are protons in this case, at an energy that can excite the Higgs field to resonate. And that calling card is resonance is called the Higgs boson. And the Higgs boson, when we formed it, is then observed by our detectors, very much like enormous microscopes. And as you know, Cambridge plays a major role in two of these detectors. So one part of the LHC physics program is to study this new Higgs field, the Higgs boson, and understand its properties, including its mass. Also, we study how the Higgs field interacts with other particle fields to give them mass, say from the heaviest particle that we know of, which is the top quark, to some of the lightest particles, for example, the muon, which is a heavy electron. It's 200 times the electron mass. And the theory also predicts that the Higgs field will interact with itself. And that self-interaction is something that we need to observe and measure at the Large Hadron Collider. So the Large Hadron Collider also focuses on other, maybe related key open questions about the universe. So I just want to mention two of them here. The first is that the matter in the universe that we observe with all the telescopes covering a large range of frequencies is only a fifth of the matter that exists. There's 5 times more matter that we don't observe, but we do see its effects. And that's called dark matter. And the evidence of dark matter astronomically we get from galaxy rotation curves and colliding galaxies. So for example, the Bullet cluster, where is an offset in the center of mass expected from that observed. Now, all of this may be related to the Higgs in the sense that some theories predict the existence of more Higgs bosons, for example, 5 Higgs bosons, and even a second set of superparticles that could explain dark matter, all of which we are searching for at the LHC. The second question is why we live in a universe made of matter when at a tiny fraction of a second after the start of the universe, you would expect equal amounts of matter and antimatter. And I'm going to leave it for Fionn to explain more about that.
Great, thank you. We'll come back to that topic.
Well, I haven't finished yet.
Okay.
So these questions and many more are being studied at the LHC. So you asked me what is happening at CERN right now. Yep. The LHC started in 2010, and we're really only at the beginning of the journey. The Collider and the 4 major experiments have successfully collected about 10% of the total data expected in its lifetime. And that's resulted in about more than 2,000 physics publications, actually. And the pandemic has actually coincided with a planned shutdown of the Collider to upgrade it and the experiments. And we now expect it to resume in February 2022. It will then take data for another 2 years, followed by another shutdown and upgrades, and follow this pattern until about 2035. And the community has also been discussing about what comes next after the Large Hadron Collider. And this has resulted in a detailed European, if not world strategy actually, for the future for a further 35 years. So that takes us to 2070 and well after my time on this earth.
Great, thank you, Val. I mean, the range of questions and issues and the size of some of those questions are absolutely fascinating. But I mean, we all hear about the Large Hadron Collider, but what's it actually like? What's it look like? I know you've got a video that was going to show us a little bit more detail about that, and it would be great to understand what it would be like to be there. Okay,
well, the Large Hadron Collider is a 27-kilometer circumference so-called circular collider, because it's actually not quite circular, and it collides bunches of protons traveling near the speed of light 40 million times a second. It has to be so big in order to reach the high energies and equivalent masses with current magnet technology. So the engineering and technological advances to build and run the LHC are immense. And as you mentioned, I've got a little video that might help put all of this in perspective. So this is a video that was produced by CERN, and CERN is situated near Geneva in Switzerland. This is an outline of where the LHC, the 27-kilometer ring of the LHC. So what happens is protons are taken from a bottle of hydrogen, they're stripped of their electrons and passed into a linear accelerator, followed by a series of ever-increasing diameter circular accelerators, where they're actually formed into bunches. So you can see that all of these circular accelerators have been used in the previous program of science at CERN. So all the infrastructure has existed for many, many years. So the superproton synchrotron is where the carriers of the weak force were discovered in 1983, and that was actually my first introduction to CERN. So the bunches of protons are injected into the LHC, accelerated and steered by superconducting magnets, and they're focused to collide where the large detectors are placed. And there are 4 detectors, Atlas and LHCb are where the Cambridge play a major role. So the raw information from the collisions, which is about 25 gigabytes per second, so it filled my laptop in 4 seconds, is then selected by the detectors and sent to the CERN data center. And at the CERN data center, there's 250,000 processor cores and 15,000 servers, and connected to the million processor cores across the world. So the data is copied and it's processed and it's distributed across the world at a rate of 100 gigabytes per second to our worldwide data grid, which enables physicists to analyze the data. And for example, in a moment, you'll see a couple of plots, which are the discovery plots for the Higgs boson. So this is, once again, a simulation of events within one of the detectors. And here are the discovery plots for the Higgs boson in 2 different decay modes. So the total amount of data that we have so far at the LHC is about 100 petabytes per year. So that's 100,000 terabytes per year. So now we're talking about exabyte scale computing. And that's the sort of problem that we're dealing with all of the data that's coming from the LHC.
Great, thank you, Val. That was super. And we'll come back to some of those themes in due course. But let me turn to Harry. I mean, Harry, this has been a tough year for all of us for obvious reasons. But if you're involved in international collaboration, and particularly with someone like CERN, and you can't get there, how's that affected your work this year? The inability to get to CERN, has it had a big impact on your research?
It definitely has had an impact, particularly across the whole collaboration. So as Val mentioned, that LHCb is currently undergoing a major upgrade. So basically the entire detector is being replaced over the next year or so, ready for the restart of the LHC in 2021. So that's, I'm sorry, 2022 now rather, it's now been delayed. So that whole program of work has been somewhat set back by the problems of getting people to CERN, getting equipment underground and so on. But on the other hand, the program is going to, so there'll be a few months delay than what was planned, but everything will still get completed. So it's looking reasonably positive. The other side is that we have a huge amount of data that's been recorded over the last 10 years. So we're busily analysing data that was recorded between sort of 2015 and 2018. And there's lots of physics measurements and searches and information that we can extract from that data. So I'm busily working away on several different analyses at the moment, working the data, so is Fionn. So there's a lot we can do in the background, and because of the way that data is distributed over this worldwide grid that Val mentioned in the previous answer, it doesn't really matter where you are in the world, you can access the data and analyze it. So there's plenty of work that you can still do, which is good, and that will keep us, people like me who work on data analysis, that will keep us busy until we start to get new data from the upgraded LHCb experiment in a year or so time.
Great. And Fionn, your PhD is all about antimatter. So tell us a bit about your research and how you investigate antimatter at CERN.
Yes, so I would firstly like to introduce the problem with antimatter. Now, the Big Bang created equal quantities of matter and antimatter. For example, for every negatively charged electron that was produced, its positively charged antiparticle, the positron, was also created. And when these matter and antimatter particles come into contact, they annihilate, leaving radiation. So the big question is, how do we live in a matter-dominated universe? And explaining this requires a flaw in the symmetry between matter and antimatter. And the current theory of particle physics does accommodate this flaw, but it still only explains a tiny percentage of the amount of matter observed in the universe. And explaining the remainder requires physics beyond the current theory. So one of the main goals in particle physics is to investigate the origin of this remainder by comparing the behavior of matter and antimatter particles. This can be done at the Large Hadron Collider, which creates matter and antimatter in equal amounts, like the Big Bang. And this enables us to study their differences in a controlled way using the LHCb detector, which is optimized to investigate matter-antimatter asymmetry. In particular, we study the particles which were present just after the Big Bang, at the time when this asymmetry originated. One of the types of fundamental particles is called a quark, and these quarks come in multiple flavors. For example, the protons and neutrons, which make up nuclei in atoms, are made of up and down quarks. However, we know that matter-antimatter asymmetry is related to the heavier versions of these up and down quarks, which are called bottom and charm quarks. And it's by studying differences between these particles containing bottom and charm quarks and their antiparticles that we hope to learn more about the enigmatic process that created matter dominance. And as a researcher, I select from all of the collisions in the LHCb detector and analyze the events which are particularly useful for understanding matter-antimatter asymmetry. These events have a distinctive signature, but they are very rare. We expect only about 2,000 in the million billion events that have occurred in the detector. So searching for these is very much like searching for the needle in the proverbial haystack. However, we will collect a vast amount more data with the upgraded LHCb detector. And this should allow us to learn much more about matter-antimatter asymmetry in the near future. And I'm very grateful to be supported by the Horo Family Foundation, who make it possible for me to do this exciting research.
Great, thanks, Fionn. Harry, we talked about your travelling, but or lack of it this year. But what about your research. So you do you're involved in the search for new physics. So explain these concepts of beauty and charm to us, and tell us, if we do discover new physics, what does it mean for the big picture for particle physics?
Yeah. Well, as Val and Fionn have both mentioned, there are a number of really big questions that we need to answer in fundamental physics. One is this problem of matter and antimatter. Another one is dark matter. And there are actually a host of other questions as well to do with the Higgs and other things. So there are lots of reasons for believing that there are more particles or more fields to be discovered than the ones we currently know about. And there are, broadly speaking, two different ways at a collider that you can go about looking for evidence of these new particles. So kind of to use an analogy, imagine that you're hunting an elephant in the jungle, and imagine there are two hunters, but they have different approaches. So one hunter goes off into the jungle, wanders around and tries to come across the elephant in a clearing, say. So that's sort of what we would call a direct search. And the equivalent of that at the LHC is something that's done by the ATLAS experiment that Andy is a founding member of, where you are looking, the way you look for a new particle is you smash protons together and you have enough energy to create that new particle, and you see the new particle itself. And that's what happened with the Higgs boson. What we do at LHCb is slightly different. So we do what are called indirect measurements. So the analogy, going back to the elephant analogy, is rather than looking for the elephant itself, imagine the jungle is very big and you don't know where the elephant is. You might wander around forever and never find it. So another approach would be to look at the tracks the elephant leaves in the jungle. So if the elephant's wandering around, it may leave footprints all over the place, and you have a better chance of seeing the footprints than the elephant itself, particularly if you don't know where to look. And that's what we basically do at LHCb. So these heavy new particles can leave, they can modify the properties of the particles that we already know about, a bit like an elephant leaving footprints. So Fionn mentioned these particles called beauty and charm quarks. So these are two of the 6 quarks that we know about. And in particular, I study the beauty quark, which is the second heaviest quark. And the beauty quark is interesting because it's very sensitive to the existence of these heavy particles. And particularly, I look at what are called very rare decays. So when you create these, we create billions and billions of these beauty particles in LHCb, and they live for a very short amount of time. They live for about 1.5 trillionths of a second, and then they decay into different particles. And there's lots of ways they can decay. But I look at the very, very rarest processes. So for example, one good example is where one of these beauty particles decays into 2 particles called muons. Now, that only happens 1 in a billion times, according to our current theories of the standard model, which is called the standard model. But if there are new particles, the rate of that decay can increase, or it can even decrease. So what we look at are measuring the rates of these very rare decays and other properties. And if we see that those properties deviate from what our theory predicts, that is indirect evidence that there are some new particles out there to be discovered. So that's a bit like seeing these footprints left in the jungle. And interestingly, in the last few years at LHCb, we've actually started to see what might be faint impressions left by particles that we haven't yet discovered. So there's this set of anomalies, as they're described, in a number of different processes involving these beauty particles, all of which deviate slightly from what our current theory predicts. So we're in this frustrating position at the moment of there's sort of tantalizing evidence there's something interesting going on, but we don't yet have the statistics, enough data to really conclusively rule in or out. So it's a bit like you've seen a sort of soft depression in the mud in the jungle. You can't quite tell if it's just a random feature of the ground or if it's actually an elephant. So hopefully with the upgraded experiment, we'll get much more, we will get much more data, and that will allow us to really clarify these anomalies. So we're in a very exciting position, and we should find out more information in the next year or two.
Great. You can hear, I mean, you can hear the excitement in your voice, and the analogy of the elephant and the footprints. I just love. I will remember that for a long time. Let me just go to a slightly different topic. So Val, gender gap. There's an enormous, well-known gender gap in sciences. One of the roles you hold in the universities as the gender equality champion. Tell us a bit more about gender equality, both at CERN and in Cambridge.
Okay, I could spend a long while talking about this and all the initiatives that are happening both in Cambridge and at CERN. But just to say, I'm a firm believer that everyone, whatever gender, race and social background, should have the same opportunities to engage with science, should they so wish. And we know that the diversity of ideas and skills really results in higher quality research. So as gender equality champion within the university, I get the opportunity to speak to the VC and people like you, Andy, about what's good practice, equality initiatives, and I work with departments to improve the diversity and inclusion. The unfortunate part of the story is, though, that in the UK, of those studying A-level physics, only about 20% are girls, even though they perform as well, if not better, than the boys, both in physics and in maths, say. So we really need to encourage and support within the schools and at home, and also expose everyone to what studying physics is like at university and potential careers it offers. Now in Cambridge, the university and colleges really reach out to help in this respect. For example, my own college runs girls-only residentials to show them what it's like to go to lectures, have supervisions and undertake practicals in the laboratory, and many of the colleges do similar things. And when the students get to Cambridge and they are undergraduates or postgraduates and they become postdocs like Harry and academics, if they're lucky, they're very much supported and mentored once they arrive in Cambridge. And they also support each other. One thing I'm very pleased about in the Cavendish is we have a thriving Cavendish Inspiring Women. In fact, it's Cavendish Inspiring All initiative, which is run by our students and postdocs. And we have speakers from all over the world to discuss all of these sorts of issues. I'm also pleased that over the past, I think it's 6 to 7 years in the Cavendish, we've recruited equal numbers of women and men to academic positions. So we also learn a lot from across the world, and working at CERN gives us a unique perspective of the issues that a career in science brings, as well as some of the solutions. And I'm also pleased to say that the Cambridge High Physics Group consists of equal numbers of men and women, with sometimes the women taking the majority, which is very unusual in this area of science.
Great. The questions are flooding in, and there's one that sort of builds on that, aimed at both Fionn and Harry, which is a bit about your personal journey. So what inspired you to get into the research topics that you did? Let's start with Fionn.
What inspired me is that it's just so interesting, trying to understand how the universe operates at the most fundamental level and how everything came to be. That's the main thing.
Great, thank you. And Harry?
I think it started off, I guess, as a kid reading popular science books, and I suppose if you're sort of slightly simple-minded and keep asking why in questions about the world, eventually you get to particle physics or cosmology. So I think it was the kind of big fundamental nature of the questions that you get to try to answer that excited me. But also a long time ago now, more than 10 years ago, when I was starting my PhD, it was just about the time that the Large Hadron Collider was about to switch on. So I actually went as a summer student to CERN in 2007, when the whole machine was just preparing to switch on for the first time. And this is a project that had been in the works for at least 2 decades, if not more, depending on how far back you count. So that the opportunity to be sort of there at the beginning of this enormous journey was really exciting as well, and has proven to be over the last decade or so.
Great. And in fact, there's a sort of related question to that, which is really for you, Val, about the anticipated lifetime of operation of the LHC. So we talked about the fact that there's regular upgrades and so on, but will we be talking, well, we may not be, but but in 50 years time, will people still be talking about the LHC, or how long will it operate for?
So the current plan is to operate the LHC till about 2035. So we've been going now, 10 years, and we've got another 15 years to go. But in that time as well, we are also preparing for the next collider initiatives. And because they take about 20 years to actually develop. And we started with the LHC in about 1990 or even before then. So it was more than a 20-year project before we even built it and started it. Yeah. So we're really thinking very far in the future, and we're looking at what's coming next. And it's most like, well, the first step in that, as far as the European strategy is concerned, is we'll be looking at a Higgs factory. So this is an electron-positron collider, whether it's linear or circular, is something to be decided. But there the idea is to sit on the Higgs, the energy of the Higgs, and produce millions of them and study it in detail. And then following on from that, the next plan is to go for this 100-kilometer future circular collider, where it really is in the discovery regime, and to answer these questions like what is dark matter, and add to the understanding of matter antimatter asymmetries and so on, is key questions that we are now studying closely in simulated form until we get to the reality of the future circular collider. But as I said, I'll be long gone then, and it'll be up to people like Fionn and Harry to run that.
Great. And there's the sort of challenging question of this was around some people arguing strongly against the building of much larger colliders because there's little theoretical evidence that newer, smaller particles can be found. Would you agree with that?
It's not about really trying to find, smaller and newer particles all the time. It's really trying to investigate the fundamentals of the universe. And to put the cost in context, because this does worry some people, I think it's about 20 billion euros to build the FCC, the Future Circular Collider, or it's something like that. And you got to ask yourself, well, what is that worth to investigate the mysteries of the universe? Because it's the only way you can do it. There's no other way to do it with current technology. But that 20 billion is over a 20-year lifetime and across the world as well. So you got to sort of put that sort of cost in context and compare it to things like the 160 billion that's spent on defence, for example, recently by the government. And then you see that actually it's not that much. And also that it can be done within our current science budget. Maybe some may ask for a little bit of uplift, but in principle it can be done. But the impact of it is enormous, right? The technological impact of all the magnet technologies, the sensors that we have to build, the computing software, and all of that, and also the skills of all the people that we do of the training for people like Harry and Fionn. They'll have all of the skills that then can go out, if they'd like to, into the outside world and take them into UK industry. So the economic impact is enormous.
Yeah, and that's an important thing to bear in mind, because of course developing these things, there's a load of innovations that you have to come up with, which can be really valuable elsewhere. We're getting close to admissions season in Cambridge, and there'll be various people doing admissions interviews. In fact, some international students have been doing them this week. And there are a series of questions that feel to me like they could be admissions questions. So I'm going to fire these at you. So Harry, the first one, is the value of the Higgs field precisely the same throughout space-time?
Yes, except where you make a Higgs boson. So if you make a Higgs boson, then the field is a different value. But yeah, and actually that's one of the unique things about the Higgs field. If you think about a magnetic field, for example, the magnetic field, if you measure it with a magnetometer, you'll see it's strong near, say, the pole of a magnet. But if you go as far away as you can into sort of deep space, far away from any sources of magnetism, the magnetic field drops to zero. And that all fields are like that, except for the Higgs. So the Higgs has a uniform value everywhere of 246 GeV is the number. And it's that uniform value that's actually responsible for giving mass to the fundamental particles, so the quarks, the electrons, so on. So one of the big questions actually we're struggling with in particle physics is why the value of the Higgs field is what it is. There's this strange effect known as fine tuning, which is, in order to get this kind of Goldilocks value of the Higgs field that we see, you have to fiddle around with the fundamental constants of nature to a really implausible degree, as if some tinker has set everything up. If you change them, the Higgs field either collapses to zero, which would mean we'd have no atoms because everything would have no mass, or it blows up to an enormous value where the whole universe would be a black hole. So that one of the big questions that actually this next Higgs factory that Val mentioned would be trying to answer is to understand the Higgs field and the shape of the Higgs field and exactly why it has this value, because it's absolutely critical to the fact that we exist at all.
Great. And then Fionn, one for you. So are there any candidate mechanisms for symmetry breaking between matter and antimatter?
Well, yes, there is. This is explained in our current theory of particle physics. So yes, there is very much a mechanism. The question is, well, we know that mechanism cannot possibly explain the amount of matter that is observed in the universe. So the question is, what is there in addition to that mechanism? As for any candidates for what that addition could be, I'm not sure. Maybe Val has some ideas.
Well, I mean, this symmetry breaking that we're talking about, that Fionn is talking about, we've seen it many times, actually. It was actually discovered in 1964 with the strange quark. And now it can be incorporated in our current understanding. It can only be incorporated if we have 3 families of quarks and leptons, which is the electron type family. And then you get this symmetry breaking in our current theory. So we know it exists. We can reproduce it in the laboratory, in the LHC. But now the question is we need it in other forms as well. And it may be, for example, in the neutrino sector, because there we're seeing indications again outside of our current theory, because we now know the neutrino has mass, where previously we didn't know it had mass. And therefore we expect some similar symmetry breaking within the neutrino sector. So we look there, we look within the quarks, and we look elsewhere as well for different violations of this symmetry. So hopefully, but there's a long way to go, because we need sort of 9 orders of magnitude more in order to explain the universe. But by studying what you do know and trying to discover new physics, then hopefully that will give us some idea what the overall answer is to the universe made of matter and not antimatter.
Great. And there's a sort of linked question here about whether it's possible that there are other parts of the universe where antimatter dominates.
Well, you can look astronomically, because wherever you have antimatter, it comes up against, there's an interface to matter. I mean, whenever they meet, they just annihilate each other. So you would see pockets of radiation coming from those places. And astronomers look for that, and there are no indications yet of extra pockets of antimatter in that sense. We also have a nice experiment, which is actually sitting on the International Space Station, called the AMS experiment. And that is measuring the antimatter in the universe as well, and all the cosmic rays that are coming through it. So that's looking for things like antiproton, anti-helium, anti-hydrogen, that sort of thing within the universe. And they're seeing some very interesting effects of anti-electrons being not quite having the distribution, the energy distribution that you'd expect, which may be an indication of what's something else, another source of antimatter, but there's no yet explanation.
If I could add something, actually.
Sorry, yes.
There's a really cool experiment at CERN called ALPHA, which is where they trap anti-hydrogen atoms. And one of the experiments they're planning to do as soon as this shutdown is over is to drop anti-hydrogen atoms through a gravitational field, because we don't actually know if antimatter falls up or down, which is, I mean, and in almost every theory says it falls down just like ordinary matter, but there are some really fringe, crazy ideas out there that antimatter actually is repelled by ordinary matter. And if that's the case, you can explain the fact there's no antimatter in the universe because it's all got repelled out of our view over the edge of the cosmic horizon. I mean, it's not very likely to be true, but it's not actually experimentally falsified yet. So it'll be interesting when they turn their experiment on to see whether antimatter goes up or down.
Great. So let me just in turn take this one, and it's a sort of broad question. I'm interested in what you think the next big discovery will be. So Fionn, let's start with you. What do you think the next big discovery will be?
Well, in terms of matter, potential for matter, antimatter, asymmetry, it's only in the last 2 years that experiments have been able to observe this matter, antimatter, asymmetry for charm quarks and neutrinos, which are another type of fundamental particle. And so the knowledge about the size of the asymmetry for these particles is very limited. So my hope is that future measurements will reveal much larger matter, antimatter asymmetry, which could explain a greater amount of the matter dominance in the universe.
Great, thank you. Harry, how about you? What do you think the next big discovery will be?
Well, I think the sort of most obvious thing from my point of view are these B anomalies that I mentioned. And my research currently, one of the things I'm working on is another test of these anomalies to see if it turns up in a different set of decays. We've got a new lecturer at Cambridge who's also a sort of leader in this area. So there's lots of results in the pipeline, which hopefully will clarify what's going on and whether these anomalies are real or they're some statistical fluke or hopefully we've not made a mistake. That's also always possible, I guess. But if they do turn out to be real, it will be genuinely, I think, one of the most exciting discoveries in fundamental physics for some decades. It'll be the first time we had real evidence of particles that weren't predicted by our current theory, which was sort of developed in the 70s and 80s and hasn't really changed much since then, although we've made lots of experimental discoveries subsequently. So that would be a really huge breakthrough. And if we see these anomalies are real, that would be a big motivation to go out and build the next collider to actually see if you can catch the elephant itself, as it were, to create these new particles directly.
Great, thank you. And Val?
Okay, is there anything left? I agree with Fionn and Harry that we need to solve the matter-antimatter problem and the anomalies. Hopefully the anomalies will be sorted in the next few years and we'll either have really discovered something new or, as Harry says, we'll be moving on and looking elsewhere. But I would also like to see the dark matter question answered. And for that, we need the LHC, we need the Future Circular Collider, but also there's a lot you can do not at colliders, and we need to search very broadly. And with all the technological advances, for example, in quantum technology, we now have a unique opportunity to really do more tabletop experiments as well. So I'm also part of a new initiative to detect the dark matter field. And this is using atoms and lasers in something called atom interferometry. It's a bit like the light and mirrors that are used by the gravitational wave experiments, the ones that you may have heard of called LIGO and Virgo. So this is a whole new way of looking at these sorts of problems, detecting ultralight dark matter, very, very light dark matter, and also measuring gravitational waves in a frequency spectrum that's never been accessed yet. But maybe that's a topic for more questions and another conversation.
That's great, thank you. And I'm really sorry to the audience. Sadly, we've run out of time. I mean, one of the things that's great about these conversations is you both get the sense of the scale of some of the questions people are asking, the passion the researchers have for their topic, but they're conversations that feel like we could continue them for a long time. And I hope we have another opportunity to do that. But for this evening, we have run out of time. Sorry we couldn't answer all of your questions. Thank you, Andy, Parker, Val, Harry and Fionn for sharing your fascinating research and ideas. There will be more of these Cambridge conversations taking place in the new year, so please keep an eye out for your invitations. And in the meantime, as I said earlier, the conversation will be posted on the YouTube channel if you want to revisit it or indeed point other people towards it. So thank you once again for spending time with us. Thank you for your continued engagement with Cambridge. Best wishes for the festive season and please all stay safe. Thank you.